Hey Calc BC, welcome to lesson 8.2, Logistic Models with Differential Equations, Part 1. This is the first of two lessons that will deal with Unit 7, Lesson 9 from College Board's version of our curriculum, Logistic Models with Differential Equations. And this is our very last College Board lesson that we're going to be doing. And by that, I mean part 1 and part 2. So by the end of 8.2 and 8.3, we'll finish this box and then we'll know the entire curriculum. So today we're going to start logistic models, and it's related to exponential models. So the model for logistic growth that arises from the statement, the rate of change of a quantity is jointly proportional to the size of the quantity and the difference between the quantity and the carrying capacity. That's a big statement. We'll be studying what that means. Logistic differential equations and initial conditions can be interpreted without solving the differential equation. That's going to be key. A carrying capacity or a limiting value of a logistical differential equation as the independent variable approaches infinity can be determined using the logistic growth model and initial conditions. And the value of the dependent variable in a logistic differential equation at the point when it is changing fastest can be determined using the logistic growth model and initial conditions. Okay, so that was a lot. We're going to get into what all that means and see some visuals and work with some equations so we'll all make sense. Let's head over to the notes. All right, so here we go. 8.2, logistic models with differential equations. In exponential growth or decay, we assume that the rate of increase or decrease of a population at any time t is directly proportional to the population p, so that the derivative equals k times p. And you can see that this curve is the result of exponential growth. However, in many situations, populations growth levels off and approaches a limiting number L. So in that case, this line right here would be a y value that we would call L, the carrying capacity. That's key vocab for this lesson. Because of limited resources. In this situation, the rate of increase or decrease is directly proportional to both P and L minus P. Remember, P is the population, L is the carrying capacity. So this type of growth is called logistic growth. It is modeled by the differential equation, dP dt equals K times P times L minus P. That will come back to haunt us, so we definitely need to remember this. If we find the second derivative, we can find out an important fact about the time when P is growing the fastest. We'll look at this in example 1. We're going to look at some examples of logistic growth, just reading about them before we get into some actual, examples using math. Before we do that, I want you to think about this equation right here. We just said that L is the carrying capacity and K is some sort of constant. P, though, is a variable, so P won't get filled in. That's going to stay there. But what's interesting here is that think about dy and dx and changing the y and the x to P and T. P is like the y, and that's really important. So P acts like a y variable, not x, when we take derivatives. So we can't just take a derivative and assume that, like a regular old chain rule, power rule, everything works like normal. We'd have to implicitly take the derivative and think about having like a dy dx, or in this case, a dp dt at the end. All right, but anyway, let's check out some examples. So this is going to be examples of logistic growth. Suppose the flu, or this might hit close to home, the coronavirus begins to spread through our school. Principal decides to have a lockdown and puts, let's say, there's 850 people, 850 students and staff members under quarantine. At first, 5 people have the flu. It spreads slowly at first and then more quickly, approaching 850 people who have caught the flu. And in this question, under quarantine means that only these 850 people are like locked into the same place. So there's no one else around. We would all be like kind of like quarantined off from the rest of society. So there's only a population total of 850 people. Eventually, the number of newly infected people would begin to slow down because there would be fewer people left to catch it, right? Some will have a strong immune system and may never catch it. And this is, what everyone's talking about when they're talking about reaching herd immunity of coronavirus is, trying to get this curve to level off because there is nobody left that hasn't already caught it. Let's look at this second version of logistic growth. Suppose a new subdivision is being built and the builders want to create a lake where people can fish. The lake has a capacity to care for 5,000 fish. A calculus student who has studied logistic growth has been hired to stock the lake with fish. He buys 1,000 fish to stock the lake. The fish multiply, and eventually the number of fish in the lake will approach 5,000. But suppose that instead someone who hasn't taken calculus and isn't very good at math is hired to stock the lake with fish. He buys 10,000 fish instead of 1,000. What will happen? This is more fish than the lake can support, so some fish will die. The number of fish will still approach 5,000, but this time from above. So it ends up looking like this versus growing to our capacity like this. Okay? The second example is a type not often given in textbooks, but this type of logistic growth curve appeared on the AP exam in 2004 and in 2008 in free response questions. Okay, so let's take a look at example 1. There's a population of fish in a lake, and it satisfies this logistic differential equation where t is measured in years. P of 0, so our population at time equals 0, is 4,000. Part A, find the limit as t approaches infinity of P of t. So this is our dP dt. Notice it looks a little bit different than our formula that we want for dP dt. In our formula, the P that's inside of these parentheses has no coefficient except a minus sign. And the P in front, there is a P in front that's factored out. So notice how we have a P in both terms here. So the first thing I'm going to do is just factor out the P. And I'm going to say that what's left over is 1 over 6,000 times P subtracted from 3. But we want this number to be 1. We don't want there to be a coefficient of the P inside of the parentheses like this. So I'm going to pull 1 over 6,000 in front. And we got to figure out what goes here. So if I distribute 1 over 6,000 to negative P, I'm going to get negative 1 over 6,000 P. If I distribute 1 over 6,000 to something, I need to get 3. So in other words, I need to do 3 times 6,000 to get the number in here. So it's going to be 18,000. And then if we do 18,000 times 1 over 6,000, we distribute, we'll get that 3 again. So that's what's going on there. But now we have essentially this number is our K, which is just a constant. But this number is our L, which is the carrying capacity. And that's a very important number to know, okay? Because if we take a look up at what logistic growth usually looks like, the function approaches the y value of L over time. It's going to approach that capacity. That's what the carrying capacity means. So when the limit as t is approaching infinity of P of t, the y value is going to be that 18,000. That's the whole point. Letter B, what is the range of the solution curve? So if we start at 4,000 and our carrying capacity is 18,000, the curve is going to start here at what we're going to call 4,000. It's going to go up and approach that 18,000. So the range, we could consider it to be from 0 to 18,000, but it's starting, time isn't not going to ever be negative. So time is here, so it's going to start at that 4,000 and then approach a y value of 18,000. So we're going to go like this, and we're going to say that the range is from 4,000, and it's going to always approach 18,000 but never reach it. And we're going to say that's for t greater than or equal to 0. Part C, for what values of P is the solution curve increasing or decreasing? So we already have the first derivative, so let's just look at it in this factored form here. The critical numbers would be P equals 0 and P equals 18,000. Okay, so I want to pause right here for a second. This is weird. This is not the normal way that we use the first derivative test. Usually in our first derivative, we have x as our variable, but remember P is in place of what y usually is. So we're talking about y values here, right? The range is y values. That's P, right? If we labeled the x and the y axis here, instead of x, we have time. And instead of y, we have P, the current portion of the population that's infected or whatever we're studying, you know, or current population of fish, potentially. In this question, it is fish. So our critical numbers are y values, but that's okay. We're just going to make a y version of a sign chart, dp dt. And so we're going to have a tick at 0 and at 18,000. And if we're below 0, let's just practice plugging in a negative number for P. It's going to be negative times a positive, so that becomes negative. Between 0 and 18,000, this number will be positive and this number will be positive. So we have positive first derivative, and greater than 18,000, this will be positive and this will be negative. So we have negative number up here. So then the range only goes from 4,000 to 18,000. So we're only talking about in here. So for what values of P is the solution curve increasing? All of them. And that's because dp dt is positive. Okay, everything else that's on this sign chart isn't even a part of our solution region, so we don't have to include it. And that is that. So I mean that tracks with this curve up here. It's increasing the whole time until it gets to the carrying capacity. It's always going to be little by little increasing, approaching that. The thing is though that we're referring to p-values, so we're saying that from here to here, the curve is increasing. We're not talking about time, which is a little weird, but that's what's going on. All right, let's try letter D. For what values of P is the solution curve concave up or concave down? Justify your answer. So let me just write down the dp dt again. So our first derivative was 1 over 6,000 P times 18,000 minus P. And, what we're actually going to want to do here is find the second derivative so we can find when we're concave up and concave down. So let's do that. We're going to have, what I'm going to do first is distribute the 1 over 6,000 P back into the parentheses so that finding the derivative is easier. So it's going to be 3P minus 1 over 6,000 P squared. So now the second derivative is going to be 3 dp dt. Remember, the P is technically the y value, so we're going to have to use implicit differentiation here. And it's going to be minus 1 over 6,000 times 2P times dp dt, which we could factor out the dp dt from and get 3 minus 1 over 3,000 P. In other words, we know what dp dt is. We just had it up here. So I'm going to just list this whole thing. So dp dt is 1 over 6,000 P times 18,000 minus P times this 3 minus 1 over 3,000 P. Okay, so that's how we're going to start. Now we're going to look for the inflection points, right? So potential inflection points happen when this equals 0. So it could be P equals 0. In this factor, it's going to be P equals 18,000. And in this one, if we set that equal to 0 and solve for p, we're going to end up with 9,000. So if we make a second derivative sign chart, and we're going to have 3 inflection or critical points type of things here, 0, 9,000, and 18,000. We got to figure out what's going on with this second derivative. So if we plug in a number between 0 and 9,000, it's going to be a positive times a positive times a positive. If we plug in a number between 9,000 and 18,000, it'll be a positive times a negative. If we plug in a number bigger than 18,000, it's going to be positive again. And we don't really care what's happening when it's negative, but it's going to be a negative times a positive times a positive. So it'll be negative down here. All right, so the point is, remember our range was from 4,000 to 18,000. So from 4,000 to 9,000, we have concave up. And then from 9,000 to 18,000, it's going to be concave down. So let me write that out. Okay. And we're justifying by saying that the second derivative is positive or the second derivative is negative. Now remember, if this was a quiz or an AP exam, just having a sign chart wouldn't be enough work. We should say the second derivative is greater than 0. And down here, we would say the second derivative less than 0. There we go. Okay, cool. Does the solution curve have an inflection point? Yes, we switched from concave up to concave down at around, well, not at exactly 9,000. So we would say yes. When p equals 9,000, the second derivative is 0 and changes sign from positive to negative. We saw that up in letter D. So we have one inflection point. The other possible inflection points aren't actually in our solution set, so we don't have to include those. Remember though, P is still Y values. Kind of weird. Okay, use this information to sketch the graph of P of T. So we know we have a carrying capacity or a cap of 18,000. So here's our dotted line that represents the maximum. We know that our initial position is 4,000. So maybe 4,000 might be right around here. And we know halfway from 0 to 18,000 is going to be 9,000. And that number is important because that's our inflection point. So what's going to happen is we're concave up at first and slope is positive. And then at some point, we're going to hit the steepest part of this curve, and then it's going to curve back down, concave down, but still have a positive slope, and then it's going to keep going that direction. So right around here, we have this inflection point. So that's really as much as we know. We never really figured out any times, any t, but this is the t-axis and this is the p-axis. So right here, though, I want to study this point for a second. This is the inflection point. And something that is fairly commonly asked about, this type of graph, this logistic curve, is which point has the steepest slope? And it's always this inflection point in the middle. That's where we switch from concave up to concave down. So we say it has the steepest slope. Something that's also true is that this inflection point where the steepest slope is always half of the carrying capacity. So I'm going to write always half of the carrying capacity. So without even doing all that second derivative work, we could have figured out that this inflection point was at half of 18,000. Okay? So in the homework, you don't always have to do the second derivative. If all you're asked to find is, you know, the concave up and concave down, you can usually just use that inflection point. That's half of the carrying capacity. All right, let's take a look at the next question. What if the initial amount is different? What if P of 0 was 10,000? What if it was 20,000? Which of your answers would change? So let's just study that for 1 second. Instead of starting at 4,000, what if we started with a y value or p value of 10,000? We'd be up here. And it's kind of like this whole curve would just shift over. So it's not like our carrying capacity would change. It's not like our inflection y value would change. So we'd actually start at this point of the curve and already be concave down. We would not have an inflection point if we started with 10,000. It would just be concave down until, you know, it approached 18,000 forever. What if we started at 20,000? We'd be above the carrying capacity. That's kind of like if we stocked our lake with too much fish that the lake can't, you know, handle all those fish. It doesn't have enough resources. So we're going to be concave up, approaching the carrying capacity from above. All right, so that's kind of what goes on with that. And the homework worksheet will give you an opportunity to explore this more thoroughly. But let's take a look at example 2, which will let us explore it a little bit. Population of fish in a lake satisfies the logistic differential equation. dp dt equals 3p minus p squared over 6,000. This is the exact same scenario. So now we're actually going to be studying this situation right now. P of 0 is 20,000. For what values of P is the solution curve increasing or decreasing? Justify your answer. So let's talk about this. If we already know, based on example 1, it's literally the same question, just a different starting point. So we know that the carrying capacity is 18,000. But this time we're starting larger than that at 20,000. So what's going to happen is our curve is going to curve down and approach the 18,000 from above forever. So let's prove that using our work. So we already know that dp dt, when we factor everything out, we get 1 over 6,000 p times 18,000 minus p. Remember, we wanted to get this into a situation where we have something times p and then something minus p in parentheses. We already know that L is 18,000, the carrying capacity. And so let's just study this sign chart really quickly. It's the same sign chart that we already had. We had critical points at 0 and 18,000, and we went minus, plus, minus. Well, this time, if we take a look at this graph, the range that we're interested in only goes from 18,000 to 20,000. It stops at 20,000 because that's where we start. It never actually hits 18,000. So that's the only range we're interested in. So we're only interested over here. So, and because of that, we are decreasing the whole time from 18,000 to 20,000. And that's because P started larger than the carrying capacity. You could also say that this is because the first derivative was negative. That would be the official region. Okay. Letter B, for what values of P is the solution curve concave up, concave down? Justify your answer. I mean, if we go back and study that second derivative again, we already found it back at the top of this page, so I'll just write it down. And if we take a look at that sign chart, we had points at 0, 9,000, and 18,000. It goes positive, negative, positive. So we're concave up for anything greater than 18,000. So it's going to be concave up for the whole region from 18,000 to 20,000. And since it's concavity, I'm not going to include the endpoint. Technically, that should be up here too. But anyway, we're concave up for the whole region because the second derivative is positive. And you can see that on the graph, we're concave up. Doesn't matter how far away we start from that carrying capacity, it's always going to be concave up, decreasing slope, just kind of like decreasing until we get to that carrying capacity. That's what's going to happen. All right, so that's what happens if we start above. Up here, this is what happens if we start below. And that's really, the key information here. What you really need to know is that formula right there. You need to know the derivative has a K, an L, a P, and a P. It needs to look like this. The variable might not be a capital P, could be something else, but you need to recognize that that is a logistic growth differential equation, and you need to know what carrying capacity means, how this all works. All right, so that is the end. Hopefully that made sense. Let me know if you have any questions. Thank you for watching.